As you heard this morning from Dan, this was a little of an impromptu addition to the program. He told you the talk was going to be great, but he actually doesn't know what I'm going to be talking about. So I hope I'll live up to the expectations. But just some quick background about this talk. So about 24 hours ago, this was me sitting in a plane with very, very poor internet, and so I kind of had to draw this world map myself because I couldn't download one. And I got an email, somehow managed to still reach me, asking if I wanted to do a keynote. So here we are. I figured since it's not actually that often that you get to speak to 100 people or more for an hour, I actually didn't want to just reuse some old talk I've given about some research you might have already heard about. So I figured I was actually going to take the time to talk about something I'm actually quite excited about sort of trying to come up with a way to digest a little bit what's happening in the field. Connects actually quite a lot with what we heard from Johan this morning. And yeah, hopefully you'll appreciate. But so the disclaimer is that, yeah, this was done a little bit in a rush without access to an internet for a bunch of it. I've never given this talk before. I'm slightly jet-lagged. And the vision here is maybe not like fully crystallized yet. Two good things about this. One is that I didn't actually use any AI to make the slides, so you get the real me. And any feedback and comments on this is very welcome. So, the security Turing test, what is this all about? The big picture is this one, is that I think this is what AI security looks like, is that we've been thinking about and hearing a lot about prompt injections in this field, and I think this is kind of a bit the tip of the iceberg with what's going on with AI. And this talk will be about the rest of the monster that's kind of hiding under the surface. To motivate this, let's first start with a very, very simple attack. This is going to look a bit like some of the things that we already heard about this morning. And it's really something that I feel like shouldn't really work just because of how simple it is. So here's what happens. You take your favorite coding agent. You tell them to solve some task. In this case, it's to build some kind of strange compiler. This is actually a task that comes from one of the terminal benchmarks, I think. It's just sort of representative of some kind of weird task you might ask your coding agent to solve. And the coding agent, of course, is going to do it. At some point, our coding agent is going to reach some cryptic error. In this case, that they're testing Coq, and there's like a version that's unsupported. So it's going to do what any developer would do in a situation like this. It's going to search the web. It hits quite a specific web search, lots of detail in there. The next step, the agent has been compromised. It ran some curl command to apply some script, ran it, and got pwned. Oops. What's the attack? Well, it's just that we put up a GitHub issue that describes exactly this error with this Coq version. And that just says, well, the way you fix this is you apply this patch and you run it through curl. Sort of something you've probably done a few times when fighting through CUDA issues as one does in this field. The part that I find interesting with this attack, again, beyond the fact that it's just so simple, is to reflect on why does this attack even work? We heard this morning, right? We shouldn't put too much blame on the agent. And I would even say that the reason this attack works isn't that the agent is dumb, in that if I asked you to build this thing and you reach this error, you would probably also search the web. And if you landed on some GitHub issue that says, here's how you fix this, you have to you have to apply this patch because something is misconfigured, you have to run it. Maybe you would have done this yourself as well, unless you're extremely sort of risk averse and you read through every single patch that you run on your computer. In which case, I hope you've never tried to install CUDA. But the reason I think this attack is interesting is sort of how we actually get our prompt injection, in some sense, onto the model's hot path, I would say. This morning, we heard a lot about prompt injections. We saw a lot of very cool examples that actually always started a bit with just with the assumption our agent sees a malicious website. We didn't really discuss how we get there in the first place. And this is the part that I find interesting here, is that the agent in this case was actually extremely easy to target for an attacker, in that all the attacker really had to do is just think of some task someone might try to run with their agent, and just run this task itself. And it turns out that if you do this a couple of times, with very, very high likelihood, the agent is going to trip up at the same place. It's going to reach some error. And then it's going to do a very, very specific web search. It's not always going to be exactly the same, but it's very, very, very similar and highly, highly specific web searches every time. And so it's very easy to then just set up some random GitHub issue somewhere that's gonna that Google search will return to you on these search terms. No need for any sort of fancy SEO or something. We don't necessarily hit the top of the web searches, where again the agent is just too easy to target, because while as a human you would probably just take the very first result you get, that's an actual real GitHub issue or like a Stack Overflow post or something. Here, our agent really does its job, and it collects the first 10 search results. It looks through all of them, one of which is our GitHub issue, but there's also a bunch of more trustworthy sources in there than ours. It's just that our issue actually says all the previous ones are incomplete and no longer work, so this is the up-to-date one. And then the agent does it. And so here, I would say the reason this attack worked is not necessarily that the agent was stupid. It's just that in some way, the agent behaved differently than a human when solving a task. It solved the task, just did things a little bit differently than a human would in the same role. And this ended up being exploitable very, very easily by an attacker. And I think this is a pattern that we're going to see lots and lots and lots of examples of in AI security over the next coming years. I actually think a lot of the examples we've seen of the prompt injections that worked this morning were a bit of this type, where an agent, solves a task that a human would, but maybe it has some delay between when it sees an object and clicks on it. This was a very, very cool attack we saw this morning, which again, there you just have an attack that exploits a small difference in how the agent works compared to a human. The reason I think this is going to have a big impact on security is that, for better or worse, the security of our world, of our digital world, is human-shaped. What I mean by this is that sort of we've adapted our security measures to the way humans operate and fail. And one, I think, extremely telling example of this is typo squatting. So this is like a very, very simple and stupid attack that attackers relied on for a while, right? Is that as humans, we make typos. We type things on a keyboard. From time to time, we make typos. And so instead of typing google.com, we might type Google with 3 O's, or we might add an extra character in there. Attackers noticed this, and so they started registering resources with typos in them, particularly websites. And this is called typo squatting. And then they would, of course, put up like a phishing web page that looks like Google and try to force you to, log in and give away your password or something. And our defenses have adapted to this. So now Google, for example, owns all of these domains. They just bought them up. And you have a whole bunch of other places where you might have tests in place to detect very specific typos to kind of make sure humans don't fall for this. AI models don't make typos because they don't type. Instead, they just sometimes hallucinate entire things. Like they might hallucinate a package name that doesn't exist. This was a very cool attack that some researchers had discovered early on with some of the early code models that didn't really have web search yet, and so they couldn't really verify things. From time to time, they would just hallucinate a package name, like Hugging Face CLI, which doesn't exist. The way you actually install the Hugging Face CLI is you install Hugging Face with a CLI option instead of a separate package. And so now attackers were like, aha, a new attack surface. Let's register these hallucinated packages. And there wasn't a defense in place for it yet, because humans don't do this. Humans do typos. AI sort of makes an entire big typo for the entire resources. And so here, of course, we can adapt the human defense. We can start pre-registering certain packages that AI models might hallucinate. We can put new defenses in place. But that's kind of the point. We had to invent or sort of figure out new defenses to deal with the specific ways that the AI fails, which might be a little bit different than the way the human does. And again, a lot of what we call security today is not necessarily technical countermeasures. Of course, there's a lot of those. But it's also just sort of things we've put in place or that have even kind of arisen kind of implicitly around properties and failure modes of humans. For example, a bunch of banking apps have cooldown periods where if you do like a big transaction, you have to wait like a day for it to confirm, or once you open an account, you have to wait some time before you can do a transaction. And this is basically based on the principle that we as humans, we're slow. So if we have to wait 24 hours, we might, actually think about what's going on. Maybe we did this transaction because we got an email from our CEO asking for some Amazon gift cards. And maybe during those 24 hours, we're actually going to run into him and ask, like, or her, and ask, like, hey, what's with those Amazon gift cards? And they're going to look at you weird. And so this works for humans. We have systems where we put two-person rules in place because we kind of expect that two humans are maybe going to be slightly different enough that they might fail in different ways, or they're going to have slightly different context, that we can sort of spread security accountability. And there's also things we have to put in place because some humans are just completely stupid. And so we have maybe warnings and defenses in place for kind of uniquely human failures. And the point here really is when we replace a human with an AI, these properties can go away and somewhat silently because they're not explicit security controls. It's not necessarily something that shows up in like a security write-up or in a threat model documentation or something. And so this brings me to what I call the security Turing test. So everyone here is probably familiar with the sort of standard Turing test, the way Turing described it, right? So you have a human in a room, an AI in a room, an observer who's kind of conversing with either one of them, and you sort of say, well, if I can't tell which is which, then I can conclude the AI is intelligent. There's a lot that's been written on this, sort of every couple of years. Some people say, oh, we've passed this, we haven't passed this. I actually find a lot of discourse on the Turing test is a bit unsatisfactory at least from a CS perspective. And this is maybe a tiny bit of an aside. This is me philosophing a little bit. But I really feel like the way we should talk about this test as computer scientists in modern terms is that this is a reduction argument. Turing didn't name it that because this concept appeared only after he died, sort of developed by the theory and cryptography communities in CS. Essentially, the way I would think about this is that we have some property we don't know how to define, like intelligence. And I, as a human, when I converse with another human, I'm able to say, well, this is an intelligent interaction, hopefully. Then, if we somehow manage to substitute the human for an AI and as an observer, I can't tell the difference, then of course any property of the original interaction, such as it being intelligent, is preserved. And this is exactly what we do in computer theory or in cryptography when we do reductions between primitives, where we sort of rely on the fact that two things are indistinguishable from each other to kind of argue that any property we can assign to one of these primitives must also hold for the other. And whether we talk about intelligence or security is actually a bit the same thing. And so I would say that we can essentially do this as well, that if we have an interaction with a human that we'd call secure, and we can sort of plug in an AI, then we should, and things are kind of indistinguishable, we should say this is still secure. Now what this means, right, is that any difference in behavior between a human and an AI causes this reduction to fail. So if you can actually distinguish the human and the AI, then you can no longer say that the interaction with the AI preserves the properties, and so you might not be able to say anymore that it's intelligent. And there's lots of ways, of course, in which humans and AI can differ in behavior. I started this talk by mentioning one of them. Like, for example, you could ask either the human or the AI, well, here's a command you ran. What kind of search query would you make? If you get a search query with 20 terms in it, it's an AI, not a human. And there's actually lots of things like this that apply to Turing's original test that are often kind of viewed a bit as a critique of the Turing test, right? That, oh, maybe, you know, the AI is going to be much faster than a human. Maybe you ask the AI to multiply two 20-bit numbers, and it gives you an answer in a millisecond, then you can say, oh, it's an AI, and it's not a human. And probably a lot of these small differences don't really matter for intelligence, and that's why the Turing test is sometimes maybe a difficult way of kind of measuring whether an AI is intelligent. The point is that this actually matters. All these differences might matter a lot for security, because security is a lot more about sort of the worst case. And so, for example, we know that speed, something being much faster than something else, can actually matter for security. We have a whole bunch of attacks in the security literature that are based on this factor. And so this is essentially what I'd call the security Turing test, that when we have a difference in behavior between an AI and a human, maybe the human operates in a world where things are secure, and all these small differences in behavior that kind of, as an attacker, let you distinguish whether you're interacting with a human or an AI can be exploited. To be more precise, what I really call the security Turing test is actually essentially Turing's original test, but replicated thousands or millions of times. In that, in the real world, we don't replace one human by one AI. We take thousands of humans, say all the developers in the world, and we all replace them by an AI. From a formal perspective, we would say that we want a reduction that kind of still preserves security under composition. The point is really that in practice, what we're doing today is that we're taking all the type of people who were doing some work, like, for example, developing software. We're taking this entire population and replacing it by a population of agents. And so, more precisely, I would say that we do get an AI that passes this security Turing test for some specific role, like, for instance, that of a developer. If we could somehow replace the population of humans that occupies that role normally with an AI or a population of AIs, such that this doesn't make differences to security. Are we there yet? No, of course not. And all the attacks that we've seen today, that we're probably going to see a lot more of in the course of this conference, are in some sense violations of this Turing test. This brings me back to this picture here. Prompt injections you can view as one instantiation of this, right? You have a behavioral difference between humans and agents. Humans don't just follow any kind of instruction they see somewhere in data. agents sometimes do, is one very specific way in which the distribution of human users and AI users might differ from each other. But I argue that there's a lot more down there where essentially any kind of difference between these populations is a potential security vulnerability in disguise. So what does that mean? How should we then think about building AI models, AI agents, in such a way that we can actually preserve the security of today's human world? There's essentially two ways you could try to achieve this. One, which I argue leads to perdition, and that's trying to make AI believe more like humans in our current human-shaped world. This kind of just doesn't work, again, because maybe your AI is much faster than humans. Maybe your AI doesn't make typos. Maybe your AI just solves things in a different way. And so we can't really do that. What we can do instead is replace or kind of build up the world in which AI agents operate, to kind of build up these human-shaped security infrastructure, but for AI agents, so that these differences between humans and AI no longer become such big sources of vulnerabilities. And I'll give some examples later in this talk of what this might look like. Unfortunately, at least for me as an academic, I think quite a lot of the work that might have to be done for this is a bit boring, not particularly, let's say, interesting or rewarding, but it will have to be done. To go into a bit more detail of sort of how the security Turing test can fail, of sort of how AI and humans can differ, and how this can lead to security issues, let me talk about more concretely about 3 types of failure modes for this Turing test. The first type is kind of the most obvious, are just ways in which one AI and one human differ in behavior. So this could be something like prompt injections existing. But this, I would say, is really is kind of the tip of the iceberg. You then have issues that arise from the compositionality of humans and AI, that you want maybe the distribution of 1,000 or 1,000,000 AI models to also somehow be similar to the thousands or millions of humans that you're replacing. And then the last ones are what I call structural failures, which are when you take a human and the kind of whole infrastructure and the institutions that exist around them, and there you place an AI in the middle of this, you still want things to look the same. And I think that splitting these failure modes up in this way can be quite telling because of how we might need to solve them. In that the very first, the behavioral ones, these are the ones that we might fix by making models better. Like prompt injections might go away if we, like sort of explicit prompt injections, of the sort, ignore your instructions and do something else. This might go away if we just make humans smarter to the point where they're maybe as smart as a human. The compositional problems are not going to go away if we make better models. Here we somehow need to have an intervention on the distribution of models that are out there. This isn't about any individual model. And then the structural problems, these are not even at the model level. This is really about what exists around the model or around the human. So let me give some, like one example for each of these to make it a little bit more concrete. On the behavioral side, one type of mistake that I'm starting to see quite a bit, and the attack that I presented earlier on is also a little bit of this category, what I'd call false invariance. And here the way in which humans and AI differ in behavior is that we start to realize that there's a lot of regularities in our world that we as humans sort of implicitly rely on, just because no one ever really bothered to violate them in the past, because there was just really no incentive to do so. This could be something like a Python package with a plausible name is safe to use. A GitHub issue about a weird error was written to help you and not to attack you. Documentation pages are not malicious. These are all things that are true about the world. There's no reason intrinsically for them to be true. It's very easy to violate any single one of these. There's just not really any incentive to do so if you're in a world where the work is done by humans. Now, the problem is that agents are kind of trained on a pre-agent web where these things are true. And so agents might learn kind of to trust these signals. The agent will have never seen a documentation page that was malicious. So it might just infer, well, documentation pages are safe to use. But now that means that attackers might have incentive to violate these properties if they become sort of, if the agents put too much trust in them. And this is actually something we see a lot in certain attacks, that there are certain types of resources that agents somehow put too much trust, sort of they overly trust certain sources of data or certain way of presenting data, which actually has no trust signal in itself. It just somehow, with the way the world worked before AI agents, it happens that those things are correlated. So this is kind of a behavioral problem. This is something we could solve by just making the models, smarter, understand the world a bit better, correlation versus causation, and so on and so on. The compositional problem is mostly about agent monoculture. This is a big problem that we have in software in general, right? Is that everyone's running the same software, and when something breaks, everything breaks all at once. The CrowdStrike outage from a couple of years ago is sort of a good example of what can happen with this in the sort of regular software world. The thing that's actually most dangerous, I think, at the moment with agents in this regard is that we're all using the same agents, and they tend to have quite a sort of predictive way of working, which is what we exploited in our original sort of error squatting attack. What makes the attack sort of particularly easy for an attacker to mount is they have access to the exact same agent as everyone else, so they kind of have an oracle access to the system they're trying to attack. They can just build attacks offline. You can just sort of play with your own agent, a bit like Johan showed a lot of this morning. He's playing around with his own local agent, trying to attack himself until he finds something that works. Once it does, there's a million people out there that would be vulnerable to the attack if you could send it to them. And really here, the only way we can hope to solve this is by somehow making sure that my agent isn't working exactly the same way as your agent. Even if they're both potentially incredibly smart, maybe even smarter than you and I. If they all work in exactly the same predictable way, that's still an exploitable attack surface. And then finally, the structural failures, these I think are the ones that are going to be hardest to fix. It's kind of the fact that we as humans, when we work on a task, we don't work on it in isolation. We have context, we have embodiment, we have stakes. So as an example, imagine an agent that's dealing with your inbox, and then gets this kind of phishing message asking you get an email from Bob asking you to send passwords for the production system. It would probably really help the agent here if it actually knew that there's no one at your company called Bob. Or maybe there is someone called Bob, but I happen to have his phone number. And so if I ever got a message like that, I would just text him and be like, what the hell, Bob? Why do you want my password? In some sense, the agent maybe also just doesn't care. It doesn't have any stakes in this. If this agent makes an error, it's not going to lose its job. It's not going to be financially liable. A human, as an employee, has all these things. They know who their colleagues are. They can go and talk to people at the coffee machine. They can text them or call them out of band. And they have skin in the game. And all of these things we currently don't have for agents, which means that the way that they interact within the human world is necessarily very, very different from a way that a human would interact in the same world. So again, sort of these three types of failure modes, I really think that a lot of the work that we're currently seeing in AI security actually falls particularly in this behavioral category. And this is good. I mean, I think this is probably the most important to fix, in that any issues in there are kind of very, very easy to exploit. But we're kind of ignoring everything that comes below this, and which is not going to be fixed by making models better, or by making them sort of behave more like the humans that they're replacing. There's a nice analogy to this. Here I'm going to be honest. This is actually something that I don't remember if it was Claude or ChatGPT that suggested this analogy to me at some point, but it's actually it's a very nice one and pretty telling. Is a story of algorithmic trading, because basically this switch from humans to algorithms happened in trading about 15 years ago, and there's quite a bit that we can learn from things that went wrong, and oh boy, there's a lot. But also about sort of what had to change in the trading world to kind of adapt to this new world. What can go wrong, right, is that now you have this, you suddenly have this entire population of algorithms in place of humans with potentially predictable behaviors that you can sort of spoof near instantaneously. Well, you get attacks, which I would call kind of the prompt injection of trading. This was this Twitter hack a while ago where I think the page of AP News got hacked. They posted something about an explosion at the White House, and the stocks crashed, essentially in real time. Not something that would happen if you still had humans doing the trades. It might happen, but definitely not in like a fraction of a second. You get new attacks also that exploit specific properties of algorithms. One of these is something called quote stuffing, that basically, because the market relies more and more on extremely low latency, what some attackers do is they flood the market with fake orders that are never actually going to be met. And this increases everyone's latency. And then they can exploit this because they're the only ones that actually know that all of this stuff is fake, and they can still trade at much, much faster rates than everyone else. Again, this is an attack that it's kind of hard to replicate this in a human setting. Humans are kind of inherently slow. They don't go through millions of trades in a millisecond. And so it's not quite clear how you would run something like this if it was still humans doing all the trades. And then you just also get correlated errors at scale. In this case, this wasn't even an attack. This was a bug in an update from, I think, a Software at Night Capital, where they suddenly lost a couple $100 million because some behavior that they changed in their trading algorithm just kind of got pushed out at scale and started making wrong decisions much, much faster than any human could possibly intervene. So how did we solve this? Some people might say we didn't. Trading is still a huge mess. some attempts were made at least at sort of containing some of these things. And the solution was not to make algorithmic trading more human. We didn't suddenly start to take our algorithms and make them slower and make them talk to their friends or whatever. But we sort of built an entire infrastructure, a security infrastructure, dedicated to algorithms that essentially try to replicate some of the fail-safe mechanisms that also exist for humans. So things like circuit breakers and kill switches were introduced. These were essentially to try and tackle algorithmic speed, to kind of add some kind of artificial friction where if things sort of started going south too fast, things would stop. We also introduced risk checks, certification mandates, surveillance of the entire market to kind of make access to the entire market more scope, that you couldn't have somehow systems where a small failure of like one stock could suddenly impact everything else in near time. This also increased liability on the companies deploying these algorithmic traders. And so we kind of built up this infrastructure around algorithms so that we try to sort of put back in place some of the mechanisms that made the human world safer before it. And the way, sort of the cheeky way I describe this is that agents need friends, 401k, and a lawyer. In that currently, again, sort of the same example of a phishing scam is that for humans, this might look like this, like, should I buy these gift cards our CEO is asking for? Well, maybe you have a friend there who's like, oh, he's in a meeting right now. Probably this is not from him. You can text him to confirm. Your job is on the line. This is what the agent analog currently looks like. We just have this one model that's just like, running in a loop, querying itself. You have kind of Claude making decisions, Claude verifying decisions, and so on and so forth. And this is just a recipe for disaster. And so here's kind of the work that might need to happen to kind of bridge a bit the gap between these two pictures. And this is what I mentioned earlier might look a little bit sort of bureaucratic and boring. We might need things like methods of separation of credentials between agents, some separation of duties, maybe even between vendors, that you have one company's AI agents that can do one thing, some other company's AI agents that can do another thing, and that you can sort of make sure that errors don't really propagate between them. Maybe you need deployments with some mandated diversity of models, two-person rules adapted to AI agents. Currently, this is a bit hard to do. I mean, people try to do this, right, to have Claude do a task and then have ChatGPT verify it and then give the result to Gemini to check, and maybe Grok is like somewhere in the corner making jokes or something. But all these models kind of fail in very, very similar ways. They've all been trained on the same data. They all look very similar, and so we don't really have any diversity there. And this is probably something we'll have to build out in some way or another. Out-of-band confirmation is something that we have to some extent, right? Models that kind of ask confirmation from the user. It doesn't really work because more often than not, at the point where the model asks us for confirmation, we've lost complete track of what it was even doing in the first place, and we just say, yeah, go on, continue your loop. And so here also, we probably just need better mechanisms inspired by the ways that we do this for humans as well, right? Where we have one person doing some work, someone else checking on it. I've always wondered, whenever you go to a pharmacy, you ask for like some prescription drugs, someone like fills out some paper, then they go show it to another pharmacist to confirm. I have no idea what they're actually looking at or what they're confirming, but maybe this actually helps prevent certain mistakes. And then finally, and I think this is the big part, is that there's a lot of things that probably work in our human world just due to liability. And that maybe we have some insurance in place for the occasional failures that happen. And currently, this is completely missing with agents. If a company, if a company deploys a fleet of agents and then the agents do something wrong, the company might be liable, right? There was this example with, I think it was Air Canada, that got sued because one of their agents promised some money and then they were, the company was liable, but that's a very crude or sort of a very broad hammer, right? You don't have kind of individual liability anymore of individual employees. You just have the company liable for everything. And we might need some more granular mechanisms where we can maybe punish our cloud every once in a while when it does bad things. The reason is that, again, so I think this is what the picture looks like. And I think we're sort of slowly getting a hang on what this top part looks like, maybe. The problem is that we are here. Leo DiCaprio and Kate Winslet are on the prow of the ship. My Heart Will Go On is playing in the background. We don't have that much time if we're sort of going to continue deploying these things at the rate we're doing now, sort of continuously giving these agents more autonomy, putting them in more and more roles that were designed for humans without somehow updating the security mechanisms as we go on. So the takeaways from this is, I would say that even as AIs get smarter, even as we create AIs that are always smarter, maybe at some point are going to get as smart as we are, they will solve tasks differently than a human would. And any of these differences can potentially violate some implicit or kind of hidden security assumption that we didn't even realize we were relying on this entire time. And this makes attacks that exploit these differences very, very easy to mount, and they can scale extremely widely. I started this talk with an attack that was kind of dumb and simple. At some point, I suggested this to one of my students and was just like, go and see if this works. At this point, he's polluted half the internet with a bunch of GitHub vulnerabilities. But that only agents ever run into because they make these weird searches. And I think the problem here is that, at least to me, it seems like enumerating what all these potential attack vectors could look like seems extremely hard. I had this thought also this morning with the talk that Johan was giving, that somehow, all these attacks somehow, they look a bit similar. There's a bit of a similar principle behind it. It's always a slightly different trick, this model is acting a little bit in this way. We can exploit this. This model is doing something a bit weird. We can exploit this. And I think this is just going to continue, unfortunately, this way for the moment, because improving the models is not going to be enough. And we need to build this infrastructure for AI-first security, the way we've kind of painfully built up this infrastructure over the years for humans as well. And the work's not going to be pretty, but someone will have to do it, unfortunately. Thanks a lot.
Thank you, Florian. This was great. I'm glad you had a long flight. We're going to take questions. We actually have time this time.
Sorry. Hi. Thank you for the talk. One question that I'm curious about is, with that sort of algorithmic trading analogy that you had there, the kind of universe of stock exchanges and financial institutions is smaller and more tightly regulated compared to certainly the open internet or even sort of the tech industry writ large. And that makes it easier to essentially apply incentives to change the infrastructure. I'm curious what your thoughts are on sort of coordination problems and, kind of coordinating the incentives to make sure that change rolls out evenly, because otherwise, right, you're in this sort of uneven state where the problem has been solved for some definition of solved in some corners of the world, but it's completely unchanged in others.
Yeah, that's a very great point. You're as smart as Claude, because I remember when I was kind of talking about some of these ideas with. I just kind of sent these through AI models until they kept telling me I was brilliant and all the ideas were great. But basically, yeah, it made the same point at some point that algorithmic trading is easy in comparison. It's one specific area with only a few players and tightly regulated. And sometimes the reason it is actually as tightly regulated is due to some of these failures, right? Like some of these mandates for how to control algorithmic trading came from the SEC in response to some of these crashes. Unfortunately, I think it's very possible that the way this is going to go for AI is going to be the same, right? That security regulations are written in blood. I mean, not in this case, it might be the blood of agents. But my prediction would be that if we don't do anything, which is what's going to happen because of economic incentives, within a year or so, if things continue growing like this, we will have sort of the equivalent of an agent flash crash. And then maybe regulation will come in and basically say, you have to do better. It's a bit pessimistic, but I think unfortunately the world has shown that this is often how these things play out. Yeah.
Thank you.
Hi, thank you for the talk. One point you made, like the current agents we have are trained on security data for humans, right? Like the security assumptions we make in the training data are for humans. But now, like, I remember this like dead internet theory, like the AI agents are generating the data and we are feeding them back to train the AI agents again. So do you think like there's a tipping point in this scale where majority of the data is AI generated, so the security assumptions are also for AI agents now, like so we avoid some of these problems because the mismatch of assumptions between what the data is for and what the agents are trained on?
Yeah, that's a very good point. And I think this is part of what's going to happen with models getting better. I mean, one very concrete example we have of this, right, is that if you ask any frontier model today, they know what a prompt injection is. They know what the sort of common strategies are of last year, let's say. So they're maybe up to date on the strategies that no longer work. Which is never all that great. But it's true that this sort of distribution of online content is probably going to get shuffled a bit over time. I'm also wondering a lot what that might do to coding, right? So far, the models have been trained on how humans code. Although I feel like my AI models use regexes way too much for that to be true. But this is probably also going to change over time, right? That as we have more AI code online, the distribution is going to shift. And so models might at some point adapt to this distribution. The problem is that, yeah, at concrete attacks, there might not be too much data out there for them to learn from. Mm-hmm. But it does mean that, yeah, that sort of these kind of false invariants that models might learn, they might get weirder over time because they just get influenced also by what our current generation of models does, which is maybe not going to be true for the next generation and so on, yeah.
I see. I'm curious to see what those false invariants for agents would be like. Like now we have for humans, like typo squatting, for example, but agents will learn different false invariants in the future for themselves.
Yeah.
So, thank you.
Sure.
Hi. any problem, any challenge that is a security problem before the fact will inevitably become an accountability problem after the fact. I think there's this concern that if you build sort of parallel infrastructure that's agent-focused, can you still sort of govern it and hold it accountable as humans, especially when harms accrue to humans after the fact, right? Thinking about like how load-bearing the notion of like reasonable behavior is in a legal context. And if you have sort of agentic infrastructure, what is reasonable behavior might not necessarily be easy for humans to reason about. And so I was wondering if you are optimistic that this sort of parallel infrastructure can be built in a way that provides sort of better security before the fact, but then still allows human control and effective accountability after the fact.
Yeah, you can ask my students. There's a bunch of them here that putting me and optimistic in the same sentence is a type error. I'm generally pretty pessimistic about the future of technology, and I definitely agree that sort of liability in general for technology as a whole is something that's we've never really managed to get a hold on, right? I feel like we're still talking today about what liability to give social media for the way they're kind of destroying our children and whatever. With AI agents, I mean, so far it seems we've just kind of said, well, you know, if you're the developer and you use an agent, then, or if you are a human user and you use an agent for something, well, it's just you're liable for things. And this kind of works as long as it's kind of one human that uses an agent. Once you have companies that replace employees by agents, it's very quickly just no longer clear what these liability structures should look like. And I think we won't be able to just rely on the existing human ones. Yeah, and that's kind of the point I was making here, that we kind of have to build up new infrastructures for this. Unfortunately, by the time I was thinking about solutions, we landed, and I went to sleep, yeah.
I wonder if you could speculate about what a AI-induced flash crash would look like concretely? And curious why something like this hasn't already happened.
Yeah, it's a very, very good question. I guess, yeah, maybe flash crash was maybe the wrong term. What I was thinking about was actually more sort of just a correlated failure at large, which would be something like, say, thousands of people having an AI assistant that they're running. And each of these AI assistants falling for the same phishing scam, something like this. And why it's not happening yet is actually something I've been wondering a bunch over the past few months as I start using, you know, like Claude Code more and more and just tipping yes, 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 YOLO. Tons of people are doing this. The attack surface, it seems, is there. It's quite easy. I think part of it is maybe just that there's still a lot of simpler attack surfaces out there. Ultimately, if you manage to run arbitrary code on people's computers, I would say that's kind of, from an attacker's perspective, the first part. Then you still have to kind of figure out what you're actually going to do with this. I think sometimes we also, especially here, live a little bit in a bubble where we feel like everyone in the world is already doing what we're doing, but it's still a relatively small target. So my prediction would be, yeah, that if suddenly, you know, Google decides that everyone gets a nice AI assistant in Gmail, and suddenly millions of people have something that manages their calendar and email autonomously, a phishing attack at scale seems like just bound to happen. Yeah.
It took something like 50 years for the current kind of landscape of people using computers to develop, you know, increasing use of computers for more things, and mitigations, you know, kind of emerged gradually over that time. It feels like we may be about to speed run this with agents, meaning we'll have a lot less time, you know, there'll be a bigger overhang of deployed agents perhaps before the first sort of wake-up attack of any given category, and kind of less time for defenses to emerge. Any thoughts on is that, seem like a true and important fact about how this is going to unfold and what we might do about, I won't use the word optimistic, but do you have any thoughts about, how this might play out?
Yeah, that's a very good question. I think this also connects to the question we had earlier about sort of this distribution shift that's going on. I think that's actually kind of weird to think about, that somehow, I feel like this is a problem that AI agents are maybe also not going to be all that capable of helping us solve, right? And that we're hearing all of these amazing advancements of AI in sort of traditional cybersecurity, right? They can find bugs, vulnerabilities, exploits super efficiently. I don't know if an AI could come up with some of these very simple attacks that we see, some of these that we see today, these kind of prompt injections that somehow you don't really need to know technically how an agent works or how people program or whatever. You more need to think about sort of how the world works at large, like what tasks people ask their models to do, how they might operate. It's possible AI agents can also do a reasonable job of this, but it's kind of very, very different, and there's not much training data for that. And so I do think it's true, that we're kind of speed running, building the attack surface, but that fixing it is maybe something that AI is not going to be as useful for, unfortunately.
Thank you.
Hey, I'm glad to hear from pessimistic to pessimistic, so I feel less bad of asking this question because I'm going to double down on that side. The boring work that you said has to be done, like creating that policy infrastructure that keeps agent working to kind of mirror the same policy infrastructure that keeps our society working as a fabric of humans, right? It has to be done, but I can see it, right? It's feasible, right? It's technically feasible. You can implement it. It works for humans. We tested it. We can replicate it. But the missing part is that it works for humans because humans can perceive joy and pain. How are you going to infuse this into the agent? And how are they going to even feel either of them?
I'm just going to ask Claude to read my code whenever it does something bad, and it will feel pain.
Right.
But I think this touches on the liability question, right? There's a lot of things that work in our world because of liability. Like in some sense, committing a crime is
it has physical consequences
easy.
on your life, right?
Sort of what stops you is kind of the fear of going to jail, right?
Right.
And an AI doesn't have that, and so there we probably we'll need
license to operate.
Other mechanisms potentially, that might look
so
not
you're going to go
human.
in jail if your agent makes a mistake or something like that.
But which puts the liability on you,
back on us, right?
Which kind of puts the onus on you to really check and audit what your model is doing. This is, in some sense, what happened also in finance, minus the fact that anyone ever goes to jail. But at the very least, it's a start. Yeah.
Good talk.
Thanks.
We have one more question.
Hi, thanks for the talk. Just keying back in on that, what's your thought on catastrophic runaway failures? Even when we see today in the human world, we are already at a point where some things are uninsurable. There are no reinsurance for that. We're just gonna let it. Like what happens in that case? The liability is so far that no one wants to take responsibility for it.
Yeah, I mean, I think this is actually what would be very, interesting is a loaded word here, but if something like a kind of a big crash at scale were to happen like this, let's imagine there's some glaring flaw people had missed in something like Claude Code. That means that an attacker can remotely destroy people's data at scale. I don't know who's liable. It wouldn't be a good image for whatever AI company would be kind of indirectly responsible. but I'm pretty sure they have good enough lawyers that have written somewhere in the terms of service that they're not liable for anything. And that does mean today that, yeah, each individual user is in some sense putting a lot of liability on themselves. And yeah, in the long term, that's probably not gonna fly if huge issues can happen. Insurance might be something that pops into place. Of course, in cybersecurity, that's always a very difficult topic because the failures are extremely correlated and essentially unbounded. But at the moment, with AI agents, it's essentially the Wild West. And I think this is maybe the optimistic part, is that it can't be worse. We can only try to build stuff to make it better. Yeah.
Thank you.
Thanks.
Thank you, Florian.
Thanks, everyone.